All right. Well, welcome back. This is Lean Together 2025, and our speaker now is Mohamed speaking about lean-SMT.
Hello
Okay.
everyone. My name is Abdalrhman Mohamed. I'm a PhD student at Stanford, and I'm here to present a project that I've been working on in collaboration with people from UFMG and the University of Iowa. And this work is about integrating an SMT solver with the Lean Theorem Prover. So let's start by talk about a motivation. So our motivation is the kind of problems that are not currently handled by the automation available in Lean. So let's say you have an example like this one here, where you have this goal that you want to prove, which is that f of x plus y is equal to f of y for some y, or for all y, I mean. And you have these constraints about the relationship between x and d. Right now, there is no like single button automation tool that can handle this in Lean right now. And our goal was to try to figure out if we could integrate the Lean Theorem Prover with other proof assistant to help with this process. Any question? Okay. So, um, and for that, there is a set of tools that have been known in other theorem provers that have been very successful in dealing with these kinds of problems, and those tools are known as hammers. So a hammer is basically a powerful automation tactic. It's being very successful in other theorem provers. In particular, like we see that 40% of the Miser math library was proven by those automation tactics. And there is, of course, also similar results in the FlySpec library in whole light and similar result in Isabelle too. So those hammers are basically tactics that integrate those theorem provers with automated theorem provers from several domains, SMT, superposition, or Tableau calculus, etc. And the hammers basically send those goals to several automated theorem provers and pick the one that gets the solution first. The components of a hammer are like it's mainly composed of three components. The first one is the premise selector that basically goes and selects the relevant premises that I need to prove the goal. And then the other two components are the translation module that basically translates the theorem provers problem in the theorem provers logic into the automatic theorem provers logic. And then the last step is the proof reconstruction module that basically reconstructs the proof. So an example of this would be the sledgehammer tactic in Isabelle. And here you see that it starts with a relevance filter that basically filters out all the non-relevant lemmas that are not going to be used by the theorem provers. And then from there, it goes and translates the problem into the proper logic and basically sends it to multiple theorem provers. And if one of those succeeds and gives us a proof, then there is a reconstruction module in Isabelle that basically returns the successful proof. So our project was basically to try to implement a component in this whole kind of workflow, which is this part here, where we want to translate a problem into SMT query that can be given to SMT solver, and then we get the result. And we want to implement this in Lean. Of course, we would like to make a few changes. First of all, we don't want to use CVC4. We would like to use CVC5, given that it has a lot more detailed proof. And of course, it's also newer and more robust than CVC4. So with that, let's go and talk about the lean-SMT tactic. So the tactic basically kinds of integrates the two worlds together, the SMT world and Lean Theorem Provers. And the way this is done is basically Lean sends a goal to CVC5, and then CVC5 solves that goal, and Lean goes and verifies that the proof generated by CVC5 for that goal is correct. To talk about this in more detail, we start with some goal in lean, and then we first of all go and pre-process this goal to simplify it such that it's kind of in a logic that's close to the one that's accepted by SMT solvers. We then translate this goal into an SMT-lib query. We send this SMT-lib query into CVC5. If CVC5 manages to solve the problem and returns unsat for the proof, like unsat for the problem, it will give us a proof for that unsatisfiability, and then we can use that to reconstruct a proof for the original goal in lean. So this is the basic workflow, and I will show this with a simple example. So suppose that we have this original lean goal that we want to deal with. So we have a problem in group theory where we just want to prove something very simple, which is the fact that the identity element is unique in any group G. So if you look at this, and we want to translate it to SMT-lib problem, we can't do that immediately, mainly because SMT-lib does not support quantifying over types or type classes or all of these extra details. For example, we don't even have an if and only if symbol. And there is, of course, some reasons for that. But in general, what we have is the fact that lean type system is very rich. It includes type classes, dependent types, higher order logic, and a lot of other things. Whereas SMT-lib theories are based on first order logic mainly, with some limited support for higher order logic. And the way to go from like higher order logic all the way down to like from lean type system all the way down to first order logic is through lean auto. So we just use lean auto to kind of to try to reduce the goal to something that we can deal with in first order logic. However, lean auto alone is usually not enough because the SMT-lib theories themselves are also very minimal. So the fact that we reduce the problem into first order logic is usually not enough. We also need to handle some other simpler cases of translation before we can call the SMT solver. For example, the SMT-lib theories do not support every operation and sort out there in first order logic. So what we do is we have these pre-processing steps to reduce those paper cuts. For example, if you have if and only if, then we can basically go and replace it with equality using the proposition extensionality axiom. And then SMT-lib doesn't have a distinction between bool and prop, so we can just embed bool into prop before sending the problem into the SMT solver. And then SMT solvers also don't support naturals, so we can kind of embed that into integers and then add, of course, the necessary assertions about the values of the integers and then send that problem into the SMT solver. There are many other examples of these paper cuts. So what the pre-processing step does is it tries to remove all of those problems before the translation. So going back to our example, we have this goal that we want to prove. If we use lean auto and some of the pre-processing steps, we end up with this goal instead, which is something that SMT solvers can handle. We basically just introduce all the the type G, and then all the actions that are needed by it. So for example, these are basically the ones that are enough to prove the theorem. And then of course, if and only if here, we just replace it with equality. The rest is about the same. So the next step is the translation, which translates a lean goal into SMT-lib query. So we start with this pre-processed lean goal, and then we translate it into this SMT-lib query. And the two are very similar to each other, thanks to the pre-processing step. So here we have a type G, we declare a sort G over there. We have, we declare some constants E and E prime. Those are corresponds to these ones here. And the operations are also available, and the assertions, the theorems that we need to prove the goal are also translated into those assertions. And then we have the final goal over here. So One thing to note about this translation, though, is that it's not always going to be sound. And we'll get back to this issue later. But like the main problem here is the fact that the logics, like Lean's logic, is not exactly the same as SMT logics. Since in SMT-lib, the types are known to be non-empty. Any sort in SMT-lib is known to be non-empty, whereas in Lean, we have to make that assumption first. In this example, this does not matter because G is in fact non-empty because it's a group and every group has at least an identity element. And then once we have the SMT-lib query, we can give it to CVC5. And CVC5 will solve this query pretty fast, and then it will return unsat with a proof of the unsatisfiability. This proof is written in CVC5's own proof format. It's called CPC. So what we need to do is take this proof and try to reconstruct it in Lean. So what we have here is, and this is the last step basically, the reconstruction takes the CPC proof and then translates it into a Lean proof. This is kind of an approximation of what it will look like in Lean, where we have assumptions and then proof steps that correspond to the ones here. One thing to note though is that we need to check this proof in with the Lean kernel. So this is important because as we said before, translation is not necessarily going to be sound, and additionally, CVC5 itself might have some bugs in it. So we go and check the proof through the Lean kernel to make sure that everything is correct. Once that's done, we can go and close the goal. So this is the overall architecture of what the tactics look like. We start with an input formula F. We pre-process it first to get a simplified version of it. We call that F prime. And then that one is basically goes through the translation layer. This is a very simple layer that basically tries to be as simple as possible to get us back to give us an SMT query. And then we use CVC5 to solve that query, and we get the proof. This is done through the foreign function interface for CVC5 and Lean. And then once we get a proof from CVC5, we go and reconstruct it in Lean. And then those two basically, and the proof that we get from the reconstructor is basically a proof of the simplified formula F prime. So what we need to do additionally is to do some post-processing to combine the proof we got from the preprocessor and reconstructor to get the proof for the original formula F. This post-processor is extremely simple. It doesn't do much work, so we'll not talk about it. With that said, we would like to go a bit more in detail about the reconstruction there. So before we talk about reconstruction, we also need to talk about the approaches that people take for proof reconstruction. There are like two known ways to reconstruct proofs in a theorem prover. One way is called proof replay, and the other one is called verified checker. So in a proof replay, what we do is we basically reconstruct the proof inference by the proof steps one by one in Lean, and we basically go and replay those proof steps in the theorem prover. An example of this would be Isabel's sledgehammer. It basically does this work. The benefit of this approach is that it's easy to implement and modify if there are some changes. Of course, it also has a disadvantage, which is the fact that it's slower than the verified checker approach. In the verified checker approach, what we do is we basically write a checker in the theorem prover, and then prove that checker is correct, and then use reflection to prove the goals that we want to work on. An example of this is the SMT coq tactic for coq, and it basically follows this verified checker approach. An advantage of this approach is the fact that it's fast. However, it's very rigid and hard to implement and modify. So for our lean-SMT tactic, we followed the first approach, the proof replay, for several reasons. One being the fact that we already have an example of a successful tactic in that in it, which is the Isabel sledgehammer. Other reasons include the fact that there is no standard SMT proof format that we can use to check SMT proofs from different solvers. So that means everything is not going to be in flux. And another reason is CBC5 itself, its proof rules are not completely stable. Like they change every now and then to be able to handle more SMT lib queries. So with that said, let's focus now on the proof reconstruction steps. A CBC5 proof, as we have seen before, is basically a sequence of steps or instantiations of proof rules. There is a lot of rules that CBC5 has in its calculus. Currently, there is 130 proof rules and additionally 360 rewrite rules that CBC5 uses. And what we need to do, of course, is to go and formalize as much of these as possible of these using lean, like in lean, so that we can actually use these proof rules for reconstruction later. And we generally follow 3 approaches for that. The first approach is we basically write a theorem corresponding to the proof rule. That's the simplest approach. Another approach is to use a tactic that basically applies a set of theorems multiple times to correspond. However, that tactic only corresponds again to just a single rule here. And then the third approach is to use reflection. And we generally use this for normalization steps where writing explaining the proof to lean is kind of harder than basically just doing the normalization and proving the correctness of that normalization. So to give an example of a theorem, we can look at the resolution rule for CBC5. So this is how it looks like. In CBC5, we basically have 2 clauses, C1 and C2 in CNF. And we apply the resolution given some pivot L and given the polarity of that literal L. And then we get the resulting clause C. So we formalize this as in the following theorem. Since C1 and C2 can contain arbitrary number of literals, we just have this represented by a list of literals, a list of propositions P's, and then we do a distinction over all of them. So this is what or N stands for. And similarly for HQs, it's the second clause. And then if we have some I and J that where the literal for I and J are basically different only by the negation symbol, then we can basically go and erase those 2 literals and get the resulting clause here. So this is a simple example of a theorem. For a tactic, in some cases, writing a theorem for a particular rule might be too hard. For example, if you look at this quantifier rule, what it does is that it goes and pushes the quantification for all x here inside for each formula. However, x here in this rewrite rule denotes multiple variables. So it could be arbitrary number of variables, 3, 4, 5, or whatever. In lean, we can go and formalize the version that only deals with 1 variable. So this is how it would look like. Again, we have an arbitrary number of conjuncts. So we use P's to represent those propositions. And then, as you can see, the theorem basically goes and pushes for all x inside. However, this deals only 1 variable. To deal with multiple ones, what we do, arbitrary number of ones, what we do is we combine it with the for all congruence rule. This basically allows us to basically peel off 1 variable at a time and apply the 2 theorems together. And then in the end, we can basically use these 2 rules to prove a theorem like this, where we say for all xy, pxy, and qxy is the same as if we push the variables inside. The last examples that we have is for an approach is reflection. This is basically a verified program that allows us to prove correctness properties about the executable program. An example that we have is polynorm, which is a tactic that basically goes and normalizes polynomials up to distributivity, associativity, and commutativity. This is an example use case of the tactic. So basically, if you see here, we have the expression on the left hand and the right hand are different, and basically polynomial simplifies, normalizes both sides so that they're equal. And the way it does that is basically by expanding the polynomials into a sum of monomials. And the way we handle the variables x, y, z in the monomials is by basically defining them as list of naturals and then allowing them to, which allows them to be compared easily. And then we prove several correctness properties about normalization. For example, we can prove that multiplying two monomials is the same as like interpreting the two monomials and then multiply them together. Similarly for a polynomial, adding two polynomials and then getting and evaluating them the same as evaluating each polynomial separately and then adding the result. And finally, we have a correctness theorem that basically says if we start with any two real expressions, this is a DSL representing the fragment that we support. And if we convert those two expressions into polynomials and the two polynomials are equal, then the denotation of the original expressions E1 and E2 are also equal. So now that we're done with all the details, I can show you some quick examples. So I have an example here of the tactic working. So basically, this is an example of interpreted functions where we have very simple stuff with interpreted functions and Boolean propositions. So here you can see that and the tactic can basically go and handle this. But this is a simple example that's basically to show you what things look like internally. So we start with the goal, false, and then we go and look at what we need to prove the goal, which are the hypotheses here. So we go and generate the SMT lib query corresponding to those. We send the query to CBC5 and it returns answer, and then it gives us this proof again in its proof format. And then what we do is we go and reconstruct this into a lean proof. And this is kind of our approximation of what it will look like as a lean proof. Of course, we can also handle arithmetic, just like I showed before in the slides. So this is some simple linear real arithmetic problem. We also support quantifiers for all and existentials. And this is basically a stress test of the tactic. And we can see that it takes about a few seconds to get it, but it's not too bad. And then this is the groups examples that I showed in the slides. This is the pre-processed version of it. And you see here that the tactic works just fine. But however, this is not how like mathematicians or anyone who wants to prove theorems about groups does things. Usually what they do is they start with the group type class G, and then use the theorems that are available already in MATLAB to go and prove a theorem. So here we integrate with lean-auto to do this work for you. So if you just provide the necessary axioms and then call lean-auto, then we integrate with lean-auto as a backend, and we basically auto calls SMT tactic to go and prove the goal. Once like auto goes and monomorphizes everything. Of course, we also can handle other lemmas, not necessarily just the one that I showed for groups, and we also support other, of course, examples like set theory here. These are some examples of set theory problems. Here we say that, well, the image of a pre-image of a set is a subset of that set. And then these are also other examples of other set theory limits that we can prove using the tactic already. Okay, now back to the slides. So the current status of the tactic is that we now support uninterpreted functions, linear, integer, and real arithmetic, and quantifiers. We would like to evaluate the tactic on some real benchmarks of lean problems. However, we don't have that set of benchmarks yet. It's a work in progress to add that we're working on. So what we evaluated the tactic on is the Isabel benchmarks that are available from other publications. And those benchmarks, of course, we can't deal with them if they're in lean in Isabel. So, but instead we deal with the SMT lib form version of those benchmarks that was generated using Sledgehammer with 1 minute timeout to just get an idea of how good the tactic is in terms of like reconstruction. And this is some of the results that we have. So here you see the total number of benchmarks. We have about 5,000 benchmarks in each set of benchmarks. And then this is the number of benchmarks that were solved by CVC5. And this is the number of benchmarks that were reconstructed by the tactic. So basically where we get the lean proof from the original like SMT benchmark. And as you can see, we basically succeed in more than 90% of the benchmarks. So with that said, now we can talk about next steps. Our first goal is to create a benchmark set for lean to evaluate our tactic and other tactics, including something like Duper and any other kind of ATP tactic available in lean. We also want to support more theories. We have some very experimental support for bit vectors. However, we would like to extend that and support other theories like data types and etc. We also need to support more proof rules. So currently we support 180 rules, but as I've shown you before, there is more than 500 rules. So we're in the process of supporting more of what CVC5 can generate proof for. And of course, there is always going to be some work that needs to be done in terms of pre-processing to reduce the paper cuts. And finally, we'd like to improve our integration with Lean Auto. And once we're done with all of that, we can go then to the next step, which is work towards a sledgehammer tactic in Lean. This is going to be, of course, a huge amount of work that needs to be done with the community. And however, the goal there is basically to reach the point where the difference between using the tactic and not using it is like walking and running, just like what Lawrence Paulson said, who's the developer of Isabel. So yeah, that's all I have to say. Is there any question?